really enjoy the conversation with the students. Let's continue the integration of ammonia, renewable power with ammonia production. So I want to finish this because the current session will be the method, how many methods exist to make ammonia different from Haber-Bosch. So let me finish this renewable power integration. Then I'm going to go to a new topic. Okay. So let's go to this. I'm going to share my slides. I need to find my slides. I have so many things open. Can you see my slide? Can you see it?
Yes.
Okay. All right. So we last session we finished here. Is that right? 111 years ago, Haber-Bosch built this way, and then the modern ammonia plant built so complex, but it costs a lot of money. All right. So now I'm going to so during the break, I did a quick search. I want to make a point, so hopefully the student understand. I will give you maybe 10 seconds to read this. Just read this slide. In engineering design, the 0.6 power rule is a commonly used rule of thumb stating that when scaling up a capacity of a piece of equipment or a plant, the cost will increase roughly proportionally to 0.6 power rule. Okay, so I want to show you a quick calculation here. It's going to be good for your student. I used to do engineering design and also estimate, and then looking at when you look at a new technology, you have to roughly have some idea on how much it's going to cost and to build. Okay, so if somebody tell you one thing, you need to have a baseline. What's the baseline? The baseline today is ammonia plant at a capacity of 1,000 tons per day. The CapEx will cost $1 billion. Everyone knows this. Okay, everyone knows. So my question to you is, what will be the estimate cost of a 2,000 ton per day plant, or what will be the cost of 5,000 ton per day? So I mentioned to you about 0.6 rule, all right? When you do the engineering design, this is a rough estimate used. Let's do a calculation. If you scale up from 1,000 ton to 2,000 ton per day, and then you double the capacity, you are not necessarily double the cost because of economy of scale. So the rule of thumb will be 2,000 divided by 1,000, and then go to the basically multiply the 0.6 power times $1 billion, and with 1.52. Remember I told you the 1 billion. So now you say that I'm going to scale it down from 1,000 tons per day to 500 tons per day, and then it's going to cost you not half. It costs a little bit more than that. So scale down is not economical because you need a lot of things, but your product sale will not offset the capital. Okay, so I don't want to go to economic, but I want to show you. So I'm going to make a point here. So I think I will send this to I think on day 4 we have case study. This is going to be case study for the day 4, and then I want to give you some of the data. I want to, instead of wasting our time in the lecture, I want you, this is more like either you call homework or I would say pre-study. I'm going to email this to Dr. Anand. Everyone look at this slide, and you will see you have to scale down the Haber-Bosch production, and because the renewable power, any solar wind farm, if you look at the energy, the production from renewable power will not sustain a 1,000 ton per day. Okay, so that means no matter what you do, even in the United States, we have so many solar and wind farms. One location, the solar and the wind, if you turn that into hydrogen, the production of ammonia is not 1,000 tons per day. So if you adopt a Haber-Bosch plant, you have to scale down. The scale down costs you a lot of money based on the calculation. I'm talking about per unit cost. So this basically force you, you have to look for the process other than Haber-Bosch, which means don't follow Haber-Bosch because Haber-Bosch costs you so much money to scale down. So you have to start a new technology. That's the point I try to make. By going through this case study, you will understand why today we want to use the microwave, we want to use the plasma, we want to use the electrochemical rather than Haber-Bosch to make ammonia. So this exercise will basically tell you the truth. Okay, you have to do the calculation. I'm not going to go through, waste your time in the classroom. I'm going to send to Dr. Nan. Okay. Right, talking about the new technology, solar and wind. So this is a little background. I'm going to show you the why we in the United States we basically started the microwave and plasma ammonia synthesis. Here's the background. If you look at the map of the United States, and then look at my circle on the left hand side. Okay, here I'm going to make a point. Okay. Let me, okay, expanded. I want to find my pointer so you can see better. So basically this is the map of US, and then if you look at this right circle in here, in this region, it's the Washington State, Oregon State, Nevada. There's so much because those are the air. There's so much open area. There's no farming in there. So the industry and then the small and the large industry company build so much solar and wind power in that area. The whole idea is to supply the renewable power to the state of California. California is here because California go green. You like every day you see the California build a renewable power plant. So that's what they want. So it's not enough. So the adjacent build so much solar and wind. But the trouble is, as I mentioned, when you build a solar and a wind farms, you have to make sure you have electricity transmission line, all right? Remember in the hydraulic, in the old days, in 100 years ago, when they built hydraulic, the power station, they build basically the power grid transmission line, but now necessary for the solar and wind because they don't consider that. So when you build so much, and then the capacity is good enough to supply the California. But today, California is not fully green. That means California power generation still depend on the natural gas. Why? Here's the why. I don't know if any student who are in a mechanical engineer or electrical engineer has ever seen the shape of this curve. It's called the duck effect. You see the duck on the side? I'm going to minimize this. Okay. So duck effect. This is something you have to watch. When you try to utilize renewable power. The shape of duck is more like this. So basically, they tell you. Let me back up. So if you look at the back to here, if you look at the capacity of solar and wind, it's good enough to supply if you calculate energy, average energy produced on daily basis. I'm talking about average. It's good to supply California. So today, California is not fully green because of this. So this is on daily demand. Daily demand, early in the morning, during the night, you demand of electricity because you are going to sleep. Like now it's like 4:40 a.m. in US. So nothing going on. The lights is off. Nobody go to work. And then you demand on the energy or electricity is flat until 9 o'clock, and then actually it drop the demand because everybody go to work, and then the demand actually drop. So after 5 p.m. when people come home, this shape more valid in the United States. I'm not sure about it in India. In India, probably it's not that deep. So because there's some just depends on how many people go to work and then how much consumption in your the manufacturing. Okay, so when you go to work and then you don't use electricity, but when you come home, your demand goes up. So after 5 p.m., see the shape like a duck on the right hand side, demand goes up. So when demand goes up after 5 p.m., I'm asking the audience, what happened with the solar? 5 p.m. Do you still have solar power? Anybody to give a try? Yes or no?
Solar power is due after 5.
Yeah. So basically, if you the after the 5 p.m. your solar stop, all right? Your solar basically producing, the starting from 9 a.m. all the way until 5 p.m. And then, but you demand this better than the demand curve, okay? So your demand is not there, but you produce. But when the demand goes up, your solar diminish. Even worse with the wind. Wind is different from solar. Wind is all depend on if the wind coming in or that there no basically windmill may not spin. So it's the intermittent nature of the solar and the wind. Either they go by the time after 5 p.m. you don't have, or during the day you have solar. No, you have a wind. You don't have a wind. Okay, so this demand curve doesn't match the supply. So there's on daily basis during the day. If you look at the supply of renewable power, it doesn't match with the demand. That's why it's called the peak. It's called the peak shaver. So there are 3 to 9 gigawatt requirement in the state of California, and then they need this power, whereas solar and wind will not be applicable. So what does it mean? So California has to go back to the combined cycle using natural gas. So this is a problem you cannot solve. So I used to ask students the question, how do you solve this question? I don't want to waste your time. I can tell you. You basically need a storage. Storage means during this time, you need a so-called green power storage. Some people say about a battery. Yes, during the day, when you have a solar and a wind running, even if there's no demand, you produce solar and the wind power, you turn that into the battery, and during the night, and then you basically use the battery to run this peak, all right, demand. That's one solution, but I can tell you, it's very expensive. The battery today is not going to be there. Two, you can store the liquid fuel like ammonia or the green ammonia or green fuel, and then the burn them during the night. That's doable. So there are a lot of solutions on this, but the problem is today we do not have those energy storage. Okay, doesn't matter green ammonia, green something to fight with after 6 p.m. demand. So what's going to happen? What's happening is the U.S. government realized all of this the solar and the wind, they are not required they are not going to supply the California because California go ahead and build natural gas the combustion plant to fight over the peak shaver. So they become either called surplus or become stranded. Stranded means nobody need it, but you put investment in there. So the whole idea for the U.S. government is to ship this electricity from West Coast all the way to East Coast. I'm going to repeat. So all this is the renewable power from shipping from the West Coast to East Coast. How do you ship the electricity? It's the transmission line, right? The grid. As I mentioned yesterday, the electrical grid are fully occupied from all the way across the continent is fully occupied. So I'm going to show you this. Renewable energy to fuel through utilization of energy. Read the title. So this is the U.S. Department of Energy solicitation. Solicitation means they want the university and the industry provide a solution. They will give you research grant funding to solve the problem. So the title of this solicitation is called Renewable Energy, which is solar and wind, to fuels through utilization of energy dense liquid. What's energy dense liquid? That's by definition. So the program is called refuel program. So I basically lead a team. So I'm the principal investigator. You see this team, the West Virginia University. You see the logo shell, and also the national lab called the Pacific Northwestern Lab, and then NETL. We have this project starting from 2016 and then operate until 2023, 6 years. So the data I'm going to show you today and then tomorrow, you will see how we solve the problem. It's still not commercialized. We are solving the problem. So the question is how we turn this wind and solar into the energy-dense liquids and then use the pipeline, the truck, transfer or transport this energy-dense liquids from west coast to east coast without using the power grid. It's more like science fiction, all right? I used to have this problem I teach another class. It's called oil gas refining chemistry. And then I used to post this and to the audience. I probably will, in the interest of time, I'm going to save this for the case study. So basically the case study will be like this. You have unlimited renewable electricity, unlimited. Just think about it, it's free. Well, by the way, renewable electricity is now free because you have to do a lot of maintenance. Okay, just think about free because it's stranded. Remember, California doesn't need it because when they need it after 5 p.m., you don't have it. So how do we transmit this electricity to another location without using the transmission line? That's number one question. But you are only given resources of air and water. What's in the air? Air has oxygen, nitrogen, and maybe a little bit CO2 and water. So think about this. I think day 4 and 5, we have, let me look at my, so day 4 and 5, we have case study. I'm going to do this as, yes, day 4 and 5. Today's day 2. And we have case study. I'm going to have this, doing a case study. So you can have a group, talk about this, and pre-class or in the class. I want somebody to tell me the chemistry and how you do that, okay? So I'm not going to tell you the answer, but I'm going to skip this, okay? So basically, so here's what I would say one of the solutions. There are many solutions. To solve the problem, this is one of the solutions I'm going to tell you, but on day 4 and 5, I want the most solution. Doesn't need to go to through the ammonia. You can go to some other liquid hydrocarbons. So this is one of the solutions I propose with this team. We received $3.1 million, and then we do this research for 6 years, and then here's the solution we have. In the water, we do electrolysis. Air, we can do separation. Air separation based on the cryogenic. Keep in mind, I give you a condition. This is the unlimited solar and the wind, is that right? If you give me free electricity, I can do the cryogenic. Basically, I freeze the air and separate nitrogen. Hydrogen, nitrogen coming out, and you make ammonia. Ammonia, which is liquid, can be transported and as energy storage by truck, by railroad. And ammonia, instead of burn ammonia, I can use as a fertilizer. So there's a lot of utilization of ammonia, but key is our proposal, which was founded since 2016, is basically using microwave reactor. Why we use microwave reactor? Because of economy of scale. Economy of scale means with the capacity of solar and wind, if we build a Haber-Bosch plant to make ammonia, it's only 100 tons per day. Remember, Haber-Bosch plant is 1,000 tons per day. So scale down Haber-Bosch 10 times costs a lot of money. So this forces us, we have to think about non-Haber-Bosch technology, which is microwave. Okay, so that I will have a lecture, 1 hour lecture, going through why microwave, how in principle microwave work in activating the nitrogen and hydrogen, and then how we change the Haber-Bosch reaction. We don't have to operate at a 250 bar, 500 degrees C. We can operate at a very low temperature, low pressure, and also we also break the thermodynamic equilibrium. Okay, so today is only just like a high level how we integrate renewable power. So I'm going to go to the detail in some other day. Remember, I mentioned about the intermittent nature of solar and wind. Remember, the solar goes down, so that means you have to shut down the ammonia production unit on daily basis. By the way, Haber-Bosch plant, because it's high pressure and high temperature, it takes you 3 days to start up. 3 days start up means you have to really slowly increase the temperature from ambient to 500 degrees C, slowly increase the pressure, and then to the 250 bar. That process takes 3 days start up. To shut down, you have to do the same thing. You have to slowly cool down the reactor. You have to slowly release the pressure. So Haber-Bosch plant startup shut down 5 days, but solar and wind only operate 10 hours. You cannot use Haber-Bosch, not just economic reasons, but from engineering point of view, it's not designed. Haber-Bosch is not designed for startup shutdown. However, microwave, you can do that. You use a microwave oven at home, all right? And then you can basically click on the button, you heat up your food for like probably 10 seconds or 30 seconds, you heat up, all right? It's quick startup, quick shutdown. But the microwave reactor in my laboratory or industrial use is different from microwave oven you have. Microwave oven you have is a box oven, but the reactor in industry or in my laboratory is really a running fixed bed or is a chemical reaction. Okay, so the reason you have such a low cost of microwave oven at home is because it's 2.45 gigahertz. It's really tuned for water. I don't want to go through that detail, but I want to tell you. So here's the other discovery. Remember, you have to deal with the intermittent nature of the renewable power. That means you have to start up, shut down every day. And then this is one of the demonstrations we have on that project. This is the project we have with so many organizations, industry partners. So you may be wondering why the Shell want to get involved in ammonia, because the Shell is the refining or the oil gas company, but they have a fossil. They are worried about the future regulation because the government will force all the fossil energy the company to adopt the green or the reduce the carbon footprint. That's why Shell constantly look for the so-called green or ammonia or green hydrogen technology. So Shell actually invested in the project. Then we have, of course, a national lab. Every national laboratory, they have the research in the lab. But this project led by myself, by me, and then West Virginia University. So anyway, so now keep in mind that we have this team putting together using microwave. We have to demonstrate quick startup shutdown. So I'm going to spend probably 1 minute on this curve to help you understand. So this demonstration on ammonia synthesis, basically we are simulate the renewable power, which has startup on daily basis. We operate at 260 degrees C and ambient pressure. So 260 degrees C ambient pressure. Remember I mentioned about Haber-Bosch process. What's the temperature? 450 to 500 degrees C. Pressure 250 bar. We can do this at ambient pressure. Amazing, all right? Largely because of the microwave. Okay, so because of microwave we can do this. Now you see we run for how many days? We run this for 9 days. In 9 days, we have so many startup. We have almost 15 startup shutdown. Let me try to interpret this curve. So if you look at the horizontal line, this are during the production. That's basically the level of ammonia in our reactor. So every time you see this the deep drop, that means we turn off the power. Turn off power means we mimic shutdown. That means, hey, we turn off power means renewable power is not available. So we say the next day we are going to start it. So you see, we have constantly we turn down the power, and then when we turn back on, and then you see the back to the horizontal line. That's what you need. So what does it mean? That means your writer has to be on and off, but every time you come back online, you have to have the same productivity. So what if this horizontal line declining? That means either your process fail or your catalyst deactivate. If your catalyst deactivate because constant startup shutdown, you will not see this horizontal curve here. You will see a downward slope. But the reason you have the horizontal curve, that means we are basically startup shutdown for 15 times during the 9 days. It's still the holding in there. So that means the process is stable. It can tolerate intermittent nature of the power generation. Make sense? Anybody have any questions? I want to
Hello, sir.
Yeah, go ahead.
In microwave method to produce ammonia, you're telling it is easy to start and stop, but in energy point of view, which is lower than hyperbore's or which is higher than hyperbore's?
Very good. So because we are heating the process, very good question, by the way. We are heating process by microwave. So this, yeah, you're right. Kinetic is low, but the thermodynamic is good. Remember, thermodynamic, you want the lower temperature so that you can achieve higher equilibrium conversion. But kinetic is low. That's right. But keep in mind, so tomorrow I'm going to show you how the microwave heating. Microwave heating is selective heating. Even if 260 degrees C, this is right temperature. The actual catalyst temperature is not 260 degrees C. The actual catalyst temperature is higher, the actual site. Follow me? Because the microwave can basically selective active site, and then the actual reaction temperature is probably 450 degrees C. Let me give you a different analogy, okay? So when you heat about the microwave selective heating, okay? So when you heat the food at home using your microwave container, okay, keep in mind, okay, your microwave container is LDPE, basically plastic. You have, let's say that in India, you eat, China, India eat rice, is that right? If you at home, if you heat your rice in a container, in the microwave oven, after maybe a few seconds, the food can burn your mouth, can go to 100 degrees C, all right? But container, you can touch with your hand. True, all right? Why?
Actually, it's heating from internal, from core of the molecule. It's not heating from. It's from into.
It's called. You just answered my question. So I think it's called a selective heating. Selective heating means, so when you heat using microwave to heat the food, you use a plastic container. Plastic is not microwave sensitive. Your food has water in there. That's why you need a 2.45 gigahertz, the microwave, because the water molecule is sensitive to the microwave. So your microwave only deal with that water molecule to heat up your food. It's called a selective heating. You follow me? So same here, because this reaction, I will show you a cartoon tomorrow. So because we use a microwave to heat catalyst, even if you see 260 degrees C here, the actual catalyst, actual site is more than 260 degrees C. Same with your food. You heat your rice in a container to 100 degrees C, but your container is only 30 degrees C, all right? So because the temperature gradient in there, because the microwave deliver energy onto your water molecule passing through the container. Same with here, the microwave passing through the microwave reactor only deliver on the catalyst. This is different from conventional heating. Conventional heating is a fire heater. Let's go by the old days, before the microwave. How do you heat your rice? How do you heat? You have to have a metal container, all right? If you heat your rice, you have metal container, put on the stove. You have a flame, heat your metal container to maybe 200 degrees C, and then the heat transfer from external to your metal container, and then your metal container heat your rice inside. It's external heating, combustion. That's conventional heating, all right? So today, when you use a microwave, you don't have to go through microwave. It's heating inside out. I'm going to repeat. Microwave deliver energy onto the molecule, heating inside out. It's dielectric heating, not to the conductive heating. You follow me? So 260 degrees C give you wrong impression, but its actual reaction temperature is higher. So kinetic is faster, actually. You follow me? Did I answer your question?
Yeah. Yes, sir. Yeah, I got it.
Actually, go ahead.
Actually, losses are minimized because we are selectively heating the particular.
Yeah.
From your
it's heat transfer is different in microwave. It's a selective heating. Selective heating, it means the microwave only heat a certain part of the catalyst inside the reactor. It's the same as you heating the food. Heating the food in the microwave oven, they heat a water molecule inside your food. That's why select heating. So it's very efficient. Microwave only look for the I would say the microwave sensitive the portion is called the dipole and heat. So I'm going to show you a cartoon tomorrow. You will see it. Okay. So it's a very good question, by the way. This is the beauty of microwave heating. So the plasma heating is different. All kinds of the way to activate the molecule. The whole idea here, you asked a very good question, is to activate the nitrogen triple bond by all means, either by temperature or by microwave energy. Okay, make sense? Okay. If you don't have any question, I'm going to switch to the topic. Actually, this is what I will talk about is also is from yesterday. I prepared so many slides on each topic, but turns out it's too many. I cannot finish. But I don't want to rush reading my slides. But that's why I want Q&A. So I want to make sure the audience digest. Okay, can understand what I'm talking about. Do you have any question? If you don't have question, if you don't have, I'm going to switch to the another topic. Go ahead. You have any question?
One more question, sir.
No question. Okay, cool. Let's do the. Okay, I'm going to close a couple of my windows so I can find the correct lecture notes. Okay. I just have so many things open. Okay, I'm going to share slides now. Hold on, I need to share the slides. Can you see the slides now? So basically, this section topic is the overview of green ammonia synthesis. We spent a lot of time on Haber-Bosch process. Haber-Bosch, remember, is a natural gas or coal gasification. You make a hydrogen, and the hydrogen you take the high pressure, high temperature reaction, make Haber-Bosch. But what I'm going to talk about here is a low temperature, low pressure but a different way to make ammonia is called green ammonia because it's a small scale, and then for the economic reason, you have to look for out of the envelope of the technology. It's very difficult to scale down Haber-Bosch the process. Haber-Bosch process has been there for 111 years, and then the people has been doing a lot of innovation, and then it's very difficult because they build. There's a reason. The point is, there's a reason Haber-Bosch the process built so large. Okay, but we are looking for small scale and using the green renewable energy or renewable energy sources. Okay, you can see my slides, all right? If you don't see my slides, just let me know because I see on my computer. I want to make sure you can see it. So the overview of green ammonia synthesis, I put a footnote here. I want everybody to read it. Okay. I want you guys to spend 10 seconds to read. So the images are used for the purpose to discuss with the students in the classroom. The slide cannot be posted online unless the copyright is obtained from the original sources. So some of these slides I did the internet search is really for the classroom illustration. Otherwise, when I teach the in person, I used to draw on the blackboard or on a whiteboard on the process. But since I'm teaching online, to save everyone's time, I don't want to draw on the slides and waste a lot of time. So I kind of cut and paste from a lot of literature. But since I'm so busy, I don't have time to cite or to put a footnotes here. For example, this one is from such and such a literature. I don't have time in there. I know it is recorded. For the student, please do not post this online. Well, let me put it this way: if you publish this on your paper or the post online, you have to give the credit or get a copyright because I didn't put a copyright on here because getting copyright from the journal takes forever. Again, I'm going to repeat this for illustration purpose, not for publication. Okay, we discuss it in the classroom. That's all the whole purpose. I hope everyone understands. Okay, so that's why I put the footnotes here. Okay, so let's see the microwave. I think now is a good time to talk about microwave, and then the why. In the last slide, I think you say 260 degrees C. I would say the kinetic is so slow, actually is not. Okay, so this slide really tell the truth. So if you look at the microwave heating is basically on the left hand side transmitter going through a reactor. Okay, so it's different from conventional heating. Conventional heating basically they go this way. The temperature. I'm drawing a line here. All right. So if I write it down. You agreed, all right? So basically conventional heating, so basically if I have I would say fire heater combustion, I want to heat this reactor, all right? So then it's either called conductive or convective heating. You agreed, all right? It's high to low. So for example, if I need this, the orange color is catalyst. Orange color catalyst. If I need this catalyst, let's say 500 degrees C, that's the low end. You agree? I have to my heat source has to be more than 500 degrees C, all right? Could be 600 or 700 degrees C, all right? So I have had either fire heater, burn very high, and then the regulate the temperature. Or I use conductive heating, but that conductive heating also high to low. You agreed, all right? I want to make sure everyone agree. Now, if I use microwave heating, it's different. That's why I use the example of you heating food from at home. Microwave go directly on active site. Keep in mind, the orange color is a catalyst. I don't have to heat catalyst. That 260 degrees C you see is a catalyst, orange color temperature. in terms of catalysis, I'm sorry, I get into deep in the weeds. So catalysis occurred not only on the catalyst, it takes place on the active site. Let's see, you have a surface of catalyst, it's called a zero oxide, and then you only need to heat active site to the temperature. But unfortunately, in the conventional heating, I had to heat my reactor, then reactor transfer the heat onto the orange color, and then the orange color, the catalyst heat active site. It's really you cascaded the temperature from high to low. But microwave heating is not. Microwave heating is my microwave. I design my catalyst active site. The active site will be talking to microwave. It's called microwave sensitive or microwave susceptible. I'm going to write this as a. It's called, you see the wording I put in here, it's called microwave susceptible or microwave sensitive. So all these active sites are designed to be sensitive to microwave. So that means my orange color catalyst can be 260 degrees C. My active site already reached 500 degrees C. Keep in mind, this reaction, nitrogen-hydrogen reaction, occurred or take place on active site. Okay, this is the beauty of the microwave, or this is the advantage of microwave. Okay, so plasma is different. Plasma doesn't heat the catalyst, but plasma heat species to high temperature. That's a different story I'm going to talk about. I'm going to pause here. I want to ask a question. Anybody understand today's topic is a different approach method to make a green ammonia. Microwave is one of methods. Tomorrow I have a full session to talk about microwave catalysis. Do you understand this slide? Anybody have any questions from audience? Microwave selective heating, microwave deliver energy onto the active site. Ask a question, please. Go ahead.
Hello, sir. Hello.
Go ahead.
One question from microwave catalysis. Actually, in microwave catalysis process, we are heating the catalyst with the aid of microwave heating, so that that catalyst alone getting heated. The gas is not heated. What I understand from your slide and from your explanation, microwave heating only applied over the catalyst. It's not applied over gas. So gas is at normal temperature. Catalyst is at high temperature.
Yes. Yeah. It's from heat from inside out. Correct. That's perfect. So basically, microwave reactor is a closed tube. It's a glass reactor. It's more like you use plastic container in your microwave oven. So basically, it's not hot. So it's transparent. So very good question. So if you look at the conventional heating, okay. Okay, so I'm going to write this conductive heating. So you agree. So you will agree. It's going to be 800. I would say 800 C, and then from the heater, and then if I point to here, so right wall. I'm going to do this. Okay, this right wall could be, I would say maybe 700 degrees C. All right. So then the orange is the catalyst. So this orange catalyst would be, I would say, probably the 600 C. And then on the orange color catalyst, remember I have active site. So you agreed, all right? So I want to make sure everybody understands what I'm doing here. So in conventional heating, let's say by conductive or convective heating, you have a heater set up at 800 degrees C. Your right wall is 700 degrees C, all right? Because the external heat transfer. Then the orange catalyst will take the heat or the temperature from the reactor wall and then maybe reaching the 500 degrees C. Keep in mind, in terms of chemistry or catalysis, reaction happen on the active site, which this is the gray colored dot, all right? You want active site 500 degrees C. So the heat transfer is from high to low. But microwave is different. Microwave actually, this reactor tube is glass. Actually, it's a quartz tube. Microwave penetrate as if you don't see it. It directly interacts with this active site, make it 500 degrees C. It's more efficient. It's exactly the same as what you are doing at home. You heat water molecule in order to heat your food. But the microwave in the research in my laboratory is not 2.45 gigahertz. It's a frequency can change. So we don't have we can activate a water molecule. We can also activate a solid catalyst active site. Different material can be induced by different frequency, different power. So basically, in microheating, so microwave general sources, we can have this 500 degrees C active site directly. Make sense? All right? It's select heating, more efficient. You don't waste heat. Conventional heating, why you have to heat 800 degrees C, whereas you only need 500 degrees C, because that's the conventional heat transfer. But in that case, you lose a lot of heat, because every time you have temperature gradient delta T, you emit the waste heat in the environment. That's why combustion heating, conductive heating will never be efficient. But microwave heating is very efficient, right? It's always the heater on the molecule on the active side. Okay, so I always joke with in the conference, a lot of the I would say the question coming from audience, they do not have the knowledge on microwave. They always say, oh, microwave heating is probably more cost more the energy than combustion heating. Okay, so let's use your home as example. When I was little, my grandma heat food using stove, either burn a coal or burn a natural gas. You put a metal container, put a food in the metal container, you heat it. That's convective heating, all right? So basically, you burn natural gas, and then today, you basically use a microwave container. Okay, that's a fact. So when I see that question, basically saying, oh, microwave costs more energy, I always joke with them, you have a microwave at home, do you? He said, yes. Have you seen your electricity bill has gone up? He said, no. I said, you answer my question. If your electricity bill because of microwave oven has gone up, that's a problem. It's a selective heating. Selective heating means it's more efficient. You only need just energy heated your food. That's it. I'm pretty sure everyone in the audience, you use microwave in school, in university, at home, all right? Do you worry about your electricity bill? I doubt. That's all because selective heating. Anyway, I'm joking, but I'm right. It's worse. I think I oversimplify microwave heating, but there's more than the selective heating, because microwave has microwave is electromagnetic field. There's electric field, there's the magnetic field. We are going to talk about magnetic field in the next couple of days. So it's more than just the heating. There's another I would say another magnetic effect causing the catalysis. Okay, all right. So this microwave is an unconventional way to make ammonia, and then that's what we are doing. So okay, let's see another way. Electrocatalysis. What's the electrocatalytic process? Obviously, you see this cartoon before. It's all about you need to revolutionize or basically change the Haber-Bosch. What's a Haber-Bosch? Haber-Bosch, basically you generate hydrogen using the steam reforming, all right? So electrocatalysis, as I mentioned, you use electrolyzer and generate hydrogen, but you still have to depend on the Haber-Bosch. Yesterday, we already talked about this, the disadvantage of this. Advantage of this, you generate green hydrogen. The whole process doesn't emit the CO2. The carbon footprint is low. You agree, all right? Because you use the green electricity, whereas Haber-Bosch, you use natural gas. But the downside or the disadvantage of this, remember we say electrolyzer is difficult to scale up, the cost of the hydrogen, and also the resources or the supply of the cathode, which is what you call that, iridium. That's there's limited supply in the world unless somebody else find out there's a reserve. But so far, based on the projection, it's not enough to supply the whole world. Okay, so anyway, the electrolysis very simple. You produce a hydrogen, and then you use Haber-Bosch. I would say this is more like a hybrid mode. It's still Haber-Bosch, only thing you change the hydrogen. It's different from microwave. Microwave, basically, you change the Haber-Bosch process. It's not going to be Haber-Bosch anymore. Okay, so let's go to the next one. If you have a question, take a microphone. Just don't wait until I ask you. Okay, so you take a microphone saying, I have a question, Dr. Hu. I'm going to stop here. So let's do a little bit more detail on electrochemistry. I know there's only one chemistry student, but I hope you mechanical engineering student still memorize you high school chemistry. So it's electrolyzer. You generate hydrogen, and then basically hydrogen and then generation is from one side, and then ammonia from the other side. So this is the innovation. Okay, it's different from here. Electrocatalytic process. Here, you only change the hydrogen production. You still feed hydrogen into the Haber-Bosch process. Now I'm talking about something different. So this process, basically, you produce hydrogen on one side, on the anode side. Then the hydrogen basically is not hydrogen, it's hydride passing through this is the membrane, and then react with the nitrogen from ammonia. It's pretty cool, all right? So I'm going to ask you a question now. So this is different. This is revolutionary change. Revolutionary change means there's no Haber-Bosch anymore. There's no the hydrogen is not from natural gas. Ammonia is not made by Haber-Bosch. Ammonia is made by electrocatalytic process. This is the ambient temperature, ambient pressure process. Okay, so hydrogen produced from one side is called the anode of electrolyzer, and then ammonia is produced from another side called cathode, nitrogen. I'm going to pause here, and then I want you to read the question. Okay, sorry. Can everyone see the question on the bottom of this? I try to shifting the. Okay, now I'm going to shift up. Can everyone see the question from the bottom? I want somebody to just stand up to answer the question. See the question here?
Yes, sir.
It sounds pretty cool, all right? Now we change the whole thing. Haber-Bosch, I'm going to repeat. You start from natural gas or coal, you produce CO2 and then hydrogen. Carbon footprint is very high. The hydrogen go to high pressure, high temperature Haber-Bosch process, you make ammonia. This process, electrocatalytic process, you don't have to make hydrogen from natural gas. You don't have to do Haber-Bosch high pressure. This is a low temperature, low pressure process. Sounds pretty cool. So look at on the anode side, you make hydrogen or hydride. On the cathode side, you make nitrogen, and then you make ammonia. So if you add the two equations together, overall, you basically produce ammonia from water and electricity. That's the advantage. You don't have to repeat the advantage. Economically, it's good. Water plus electricity, you make the ammonia. There are no external added hydrogen. What are the challenges? I want people to tell me the challenge, a couple challenges.
We need to depend with hydrocarbons for generating hydrogen. So we are environmental point of view, we are safe.
Very good. Keep on going. Yes, very good. Any other disadvantage of this? Sounds pretty cool. All right. Why today you don't see that this is the in the commercial?
Sir, here one more challenges is there. That is when we are not adding the H2 externally from the water for forming the ammonia. So there will be the possibilities of hydrogen evaluation reaction.
Oh gosh, thank you. Wow.
That
Can you tell me your major? This is great. Oh, I didn't expect the students say this. What's your major? Can you tell me your major or research area?
I am mechanical engineer.
Wow, gosh, I really appreciate it. Normally the chemistry or chemical engineering student use that terminology. It's called hydrogen evolution. I'm so happy. Mechanical engineering student, you understand this. Okay, perfect. Let's do this. Thank you. I really
We compete with the nitrogen so that that formation rate may be reduces.
thank you. Very
Yeah.
good.
If it is,
Keep on going. Keep on talking. Yeah, go ahead. Yeah.
Yes, sir. If it is readily available, that hydrogen molecules for the nitrogen, so it will be combined easily so that it can easily form the ammonia. So for forming the ammonia, so if we have the hydrogen evaluation reaction, that will be compete with the what is it, the nitrogen, so that will not get the much more amount of hydrogen, so that ammonia production rate will be reduced. That will be the challenge, sir.
Thank you. Another chance. Okay. Very good. So I hope everyone hear what he said. Okay. Very good. So if you look at the diagram before I don't look at the word I put in on the upper right hand side. Okay. So if you listen what this student said, very good. I really like this student. Talk about this. It sounds pretty cool. All right. So water electrolysis. Keep in mind what you want is water electrolysis. You want that hydride. Okay. Look at this hydride. No, not hydride. Proton. You want is a proton. The proton has to go through the membrane. It's a liquid. This liquid or aqueous phase reaction. Go to membrane. Go to the other side of electrochemical reactor to meet with the nitrogen, and then to react to form ammonia. Everything go under this is the aqueous within the cell. You heard our students say that, right? It's called hydrogen evolution. But this proton or the hydrogen doesn't listen to you. So the tendency they come out as H2 because that's given. If you do the electrochemical, so-called look at the potential, it's so easy for hydrogen to evolve as H2 rather than going through this side to meet with the nitrogen. Hydrogen in water doesn't like it because the moment you break it, they said, okay, I want to come out as H2 rather than hydrogen. That's challenge. So now another challenge is N2 activation. Remember, nitrogen N2 is a triple bond, all right? Haber-Bosch 100 years ago spent so much effort running 4,000 experiments, okay, to come up with that condition, high temperature, high pressure. And over the 100 years, everyone tried to do innovation. And everyone want to activate nitrogen. Even microwave I talk about, the whole idea is to activate nitrogen on the catalyst. So the challenge here is low temperature, even lower ambient temperature. There's no temperature. You are relying on the cathode, catalyst, and also electricity, and then to activate nitrogen. It's very difficult. So I can tell you, I can show you the data. So from this process, the yield, I know we are running out of time. We are going to continue. I'm going to finish in 1 minute. So the yield of the ammonia is a ppb. You even don't see it. It's parts per billion. So that means you barely see nitrogen. Most of hydrogen coming out from this side. If you want to analyze the ammonia, it's a ppb level. What's the meaning of ppb level? It takes you 3 days to get 1 data point. 3 days, 1 data point. It's not economical. And then not only that, in order to run this reaction, you have to overcome hydrogen evolution. For the same student, can you answer my question? how do you control the hydrogen evolution? My question, what if I do not want hydrogen evolve? I want hydrogen to be inside the electrical cell, electrochemical cell. How do you overcome hydrogen evolution? Can you answer my question, or do you know the answer? If you don't, I can tell you. Can you give that student the microphone? How you control hydrogen evolution? Hydrogen evolution is bad. How do you control that?
So we can, there are two possibilities. One is we can increase the nitrogen reduction reaction so that all the hydrogen ions will be easily mingled with the nitrogen, possibly can form the ammonia. And the second thing was for the hydrogen evaluation. So we can effective, or else we can we can increase the that is the electrical supply, so that in such a way that can easily that is disassociate the water molecules, so that the hydrogen ions will be easily obtained.
Thank you. So basically, I don't know if the student understand what he said. Okay, I understand. So I want to interpret what he said. So basically, this student answers very good. So he look at the equilibrium point of view. If you look at the two equations on anode, the cathode, so the solution will be, if you want to increase the liquid phase reaction, do not let hydrogen come out from gas phase. So there's several ways to do this. So first answer, he said, we increase the ammonia production. That means you drag the equilibrium from the to the right-hand side. When ammonia going this way, they drag the hydride. When you have hydride moving from the left to the right, so they basically shift the direction. That's a very good answer. In order to do so, you have to make anode and cathode super active. Super active means they are the kinetic very fast. That's catalyst. You have to develop a catalyst, put on cathode to enable faster kinetic of this reaction, to enable fast kinetic of this. There's another way from the engineering point of view, or if you look at system engineering, to overcome hydrogen, it's called overpotential. Overpotential means you basically put a reverse, you put the so-called high voltage on the electrical cell, and then basically inhibit hydrogen formation. You can do that. It's called overpotential. That means you basically have the high voltage just to counter on the hydrogen formation. There's a terminology in there. But increase the voltage, of course, you spend more energy, all right? So there's a lot of disadvantage on this, but there are advantage will be you don't need the hydrogen. It's a revolution change. So a lot of innovation needed, catalyst, design the cell, and also a lot of things. I'm going to stop here. Tomorrow we are going to continue. There are some other the technology we need to go through, and then to make the green ammonia. Okay. Yeah. Thank you, everyone. So I'm sorry we run out of time a little bit today. Yeah. So.
Thank you.
Good. Right. So the tomorrow, I think Dr. Anand will send me the email. Tomorrow will be the same time. There are 2 sessions starting from same time, right? So.
Tomorrow sessions link, everything we will email you, sir.
Yeah, tomorrow link will email to me, correct?
Yeah. As like
same time.
Yeah.
Okay. All right. Thank you. Yep.
Thank you.
See you, everyone. Yep.
Yeah. Have a nice day, sir.
Thank you.